Alright, here we go. This is the last video in the kinetics unit, and we're going to talk about something that's going to blow your mind. So, hate to disappoint you, but most reactions do not occur in one step. All of those reactions that we've been writing as just reactants turning into products, straightforward like that, it doesn't really work that way. That's like saying if you throw some eggs and some flour together, you get a cake instantly. There's some steps in between that have to happen. But we just think, if I give some eggs and some flour to Mom, I'll get a cake. We don't really consider the steps that happen afterwards. So let's think then, or let's take a look then at a reaction like this one. We have nitrous oxide reacting with oxygen to produce nitrogen dioxide. This reaction actually occurs in two separate steps. So let's think about why this couldn't occur in one step. If we looked at the balance reaction, we've got two nitrogen oxides. Let's draw those. So those would look like nitrogen bonded to oxygen, and we have an oxygen, which is two O's. So in order for this reaction to occur, and we have two of those, so what's going to happen in order for reaction to occur, in order for NO2 to form, is each of these nitrogens is going to have to catch onto one of these oxygens. So that nitrogen would gain that oxygen to become NO2, and then this nitrogen would have to grab onto that oxygen to become NO2. However, what this requires then is for both of these nitrogen oxides to hit a single oxygen molecule at the same time, because this one can't come over and take the oxygen and just leave that one packing. This oxygen won't accept that. It wants to have its own NO before it's going to give up its bond right there. So that means that both of these would have to hit N to O at the same time with the right amount of energy. Something like that actually happening, the statistics are staggering. It couldn't occur. So what that means is in order for this reaction to happen, something in between has to happen. So something to make this process simpler. So here's what scientists have proposed will happen for this reaction. The first thing that's going to happen, so the first step is those two NOs are going to actually react with themselves. So NO plus NO, and that's going to form N2O2. So that molecule, the N2O2, forms, and then it itself goes on to react with the oxygens. And then it can react with those oxygens to form two NO2s. So what happens then is the nitrogen oxide, nitrogen oxygen, this guy right here, reacts with itself to form N2O2, and then that same N2O2 goes on to react with oxygen to form that guy right there. So N2O2 is created, then used up. It's what we call an intermediate. An intermediate is a molecule that's created but then used up, so we don't write it in the overall reaction because it's really not there for all intents and purposes. We create it, then destroy it. This is like the batter that makes a cake. You start with eggs and flour, you make a batter, you get a cake. But nobody ever really considers the batter. We just look at the beginning and then the cake. So then the overall reaction, that would just be the sum of the two reactions. We see that two NOs react to form oxygen, and that produces two NO2s. And so that's the balanced equation. That's the one that we're always concerned with. That's what we've seen in general chemistry. Those are the ones we balance and write out. We don't typically consider the intermediates that happen. This, what we're looking at, is what's called a reaction mechanism. So it's the process by which a reaction actually occurs, showing all of the steps in between. And these steps right here are called elementary steps. I don't know how to spell elementary, so I'm not going to write it down. I'll let you write it in your notes. And so these intermediate steps, these elementary steps, what they allow the molecules to do is actually form their reaction a lot easier. We think about what we looked at before, how the two nitrogen oxides would have to hit the oxygen molecules at the same time with the right orientation. By forming this intermediate, they bring those two NOs together so that when they hit the oxygen, they'll be hitting the oxygen together, and then they can form their molecule. So it makes it so this reaction can actually occur. So those intermediates, like the dinitrogen dioxide in this guy, they're usually really, really unstable. So they don't last long at all. They'll go and find someone else to react with, or they'll break apart. And in this case, it's finding the oxygen to produce those guys right there. So they're very, very unstable and are produced and consumed. So we don't write them in the end reaction. But when we talk about mechanisms, we can write those in and we can see how they happen. So I'd like to propose a thought to you guys. Let's look at that reaction that we've been talking about. So two NOs react with oxygen to produce two NO2s. So this particular reaction we saw goes through multiple steps. If we think of the rate law for this reaction, so the rate would equal the rate constant times the concentration of NO raised to its particular power times the concentration of O2 raised to its particular. So what we can get from this then is how the rate is affected by the concentration of nitrogen, oxygen, nitrous oxide, or the concentration of oxygen, based upon whatever order they are. So by increasing the concentration of this, it will have this factor of an effect on rate. By increasing the concentration of this, it will have this factor of an effect on the rate. What it turns out, the rate law for this guy is that with respect to nitrogen oxide and with respect to oxygen, it is second order with respect to NO, and it is zero order with respect to oxygen. What that means is if you change the concentration of oxygen, it will have no effect on the rate. You could have the most concentrated solution of oxygen, and it would not affect the rate. You can decrease the amount of oxygen in the system, and it wouldn't affect the rate. The nitrogen, oxygen, the NO, when you increase that concentration, it has a factor of 2 effect on it. So that means if you double it, it's going to quadruple the rate. If you quadruple it, it's going to multiply it by 16, so it has a huge effect on the rate. Why is it that NO has such a huge effect on the rate, but oxygen has no effect on the rate? Why is it that changing the concentration of oxygen does not change the rate of reaction? I've piqued your guys' curiosity, I can tell. Well, I'm going to answer that question here in the next couple slides. So let's go ahead and consider a different reaction. This reaction shows nitrogen dioxide reacting with carbon monoxide to produce nitrous oxide and carbon dioxide. The rate law for this one, which can only be determined experimentally, so it's not something that we can find using a balanced equation or even just thought. We have to do an experiment to figure these out. So a scientist somewhere did an experiment and found out that the rate, so the rate law for this reaction, is the rate equals whatever the rate constant is, times the concentration of NO2 squared, times the concentration of carbon monoxide raised to the 0 power. What that means is it is second order with respect to nitrogen dioxide and 0 order with respect to carbon monoxide, which means that the value of carbon monoxide would just be a 1 no matter what the concentration is, so it's going to have no effect on the rate whatsoever. So then once again, why is that? Why is it that even though carbon monoxide is a reactant, so it's not an intermediate or something, it has no effect on the rate? NO2, though, has a doubling or a second order effect on the reaction rate. So here's why. The overall reactions, you're right, we can't figure out the rate law just from looking at the equation, but we can figure out the rate law from looking at the elementary steps. So here, if we break apart this top reaction, so the nitrogen dioxide reacting with carbon monoxide to produce nitrous oxide plus carbon dioxide, if we break it apart into its steps, so the first step would have the nitrogen dioxide reacting with itself to break apart into NO and NO3. Step number 2 would have that NO3 reacting with the carbon monoxide to produce NO2 and CO2. So if we think of this in terms of the overall reaction, we can see that nitrogen dioxide breaks apart into NO and NO3. That NO3 is consumed, created and then consumed, so that would be an intermediate. And then we have 2 nitrogen dioxides on our left side, on our reactant side, and 1 on our product side. So that means this nitrogen dioxide is going to cancel out one of those nitrogen dioxides. So in the end, our overall reaction is NO2 plus carbon monoxide yields NO plus CO2, just as we've seen up here in the overall reaction. So these elementary steps yield this overall reaction right here. So if we take a look at the rate laws for the intermediate steps, we can figure out the rate law for an elementary step by looking at its balanced equation in the elementary step. So we can't do this in an overall reaction, but we can do it with an elementary step. So let's take a general reaction of A plus B, yielding C plus D, where the lowercase letters are the balancing coefficients and the capital letters are the molecules themselves. So then the rate for an elementary step, and this is just for elementary steps, okay, so do not try and do this for a regular step, for an overall reaction. The rate for an elementary step is going to be the rate constant times the concentration of A raised to the power of its balancing coefficient times the concentration of B raised to the power of its balancing coefficient. So if we look at step number 1, its rate would be the concentration of NO2 squared. And that's because the balancing coefficient on NO2 is 2, so we would square it. And the rate of the second step would be the rate constant times the concentration of nitrogen trioxide times the concentration of carbon monoxide. So there's two different rate laws, one for each step. We can see that the rate law from step number 1 matches the rate law for the overall reaction we saw in the last slide. So this rate law for this step matches the overall reaction's rate law, where it was K times NO2 squared, where it was second order with respect to NO2 and 0 order with respect to carbon monoxide. What scientists can derive from this then is that step number 1 is a very slow step, or relatively slow. It's slower than step number 2. So we would say that step 1 is a slow step and step 2 is a faster step. We would say then that step 1 is a rate determining step. Think of this as people running in a straight line. If the person at the front of the line is really, really slow, it doesn't matter how fast the other people behind them are. They're not going to be able to go any faster than that slowest step. So this reaction, the rate of this reaction, is determined by the slowest step. Even though step number 2 is fast, and it could be really fast, it could be lightning fast, like instantaneously fast. But if step number 1, which is providing the reactants for step number 2, is slow, that means the reaction is going to be determined by step number 1. Because if it can only produce NOs and NO3s, like 1 every 5 minutes, even though this guy can use them up, it can eat them up really, really quick, it's not going to be able to because this guy only produces 1 every 5 minutes, so this reaction can only happen once every 5 minutes. So since this is the rate determining step, it determines the rate law. This is why the concentration of NO2 affects the rate, and it affects it by a second order, but CO has no effect on the rate, because if you increase the CO, it's not going to speed this reaction up any. It's not going to have any effect on the rate determining step. So therefore, CO, carbon monoxide, which is not part of the rate determining step, is 0 order. NO3 is created and consumed, and it's not part of the reactants in the rate determining step, so it is not going to be in the rate law at all. So we can figure out what the rate law is by looking at the reaction mechanisms, determining who's the slowest step, and then writing the rate law for the slowest step. That rate law would match the rate law for the overall reaction. So let's take a look at this reaction that I proposed to you at the beginning, or that I showed you at the beginning. I had told you that the rate law for this guy was equal to, obviously, the constant times the concentration of NO squared, and it was 0 order with respect to oxygen, so we don't even write it in the rate law equation. Let's take a look at those elementary steps then that make this reaction the overall reaction. So it was 2 NOs reacting with themselves to form N2O2, and then N2O2 goes on to react with oxygen to produce 2 NO2s. So let's write the rate law for each of these steps. The rate law for the first step would be equal to the constant times the concentration of NO, and there's 2 of them, so we would square it. The rate for the second step is going to be equal to the constant times the concentration of N2O2 times the concentration of O2. And if we take a look at our rate laws here, so here's the rate law for the first step, here's the rate law for the second step. The rate law for the first step matches the overall rate law with K times NO2, so those two are a perfect fit. And if we take a look at the second step, it has rate equals K times the concentration into O2 times the concentration of O2. That doesn't match with our rate law at all. So the question I would propose then, which one of these is the slower step? If you said step number 1 is slower, you would be correct. Step number 1 is slower, and step number 2 would be relatively faster. So we would say that step number 1 for this reaction is the rate determining step. Since it's slower, it's going to slow down the entire reaction, and that's going to determine what the rate is. So this is why oxygen is 0 order for the overall reaction. You can increase it all you want. You can increase it to a huge amount, and it's not going to affect the rate because it can't speed up that first reaction. If you add more nitrogen oxide, nitrous oxide, that will increase the rate because you will increase the speed of the rate determining step. By increasing the concentration, you increase the chances of collisions, and so you speed up this step, and speeding up that step speeds up this step, and so therefore it'll speed up the overall reaction. But just increasing one of these will not increase the rate. Something I don't want you to think from looking at these two examples is that the first step is always the rate determining step. Not the case. It just happened to work out this way. But occasionally it might be the second step that's slower, and it'd be the same thing then. So if this step was faster and this one was slower, the reason it couldn't proceed any quicker is because even though this one might be really quick, this one's too slow to use up what's being produced by this guy. So the rate determining step could be the first one, could be the second one. Sometimes there's even third and fourth steps in this, and one of those would be the rate determining step. It doesn't matter where in order they fall. But the slowest one is the rate determining step. The rate law from the rate determining step is the rate law for the overall reaction. So this is the take-home point, and this is kind of the cool thing. So chemists determine rate law through experimentation. So we've looked at experimental data and how you would use that data to figure out what a rate law is. Once they know what that rate law is, they can use that to figure out what the elementary steps are. So it's not like we can zoom in on a chemical equation and watch, okay, so those two NOs form an N2O2. Scientists have to make predictions, they have to make hypotheses based upon what they observe from the rate law. So they would figure out the rate law from that reaction we were looking at, and they would see, okay, increasing the concentration doesn't have any effect on the rate, which means that the oxygen is not part of the rate determining step. So what's a method by which this reaction could occur that would use 2 nitrous oxides and no oxygens to produce elementary steps and then give us our final product? So once they know what the rate law is, they can use the rate laws to tell them which is the slowest step, and they can then use that to figure out what the fast steps are. And that's how chemists are daily making your life better and this world a better place to live in.